7.3 for this chapter deals with how earthquakes cause damage and what we can do to try to reduce the amount of damage that happens. Well, the first statement here that I've highlighted, that earthquakes are most dangerous when they occur near people, that makes more sense. If it happened in the middle of nowhere, it wouldn't affect too many people, but if it happened in the middle of a downtown city, that would affect a lot of people. Well, we usually measure things on the Richter scale, which is measuring how fast the ground moves at a seismic station. Now, today, scientists like to use this moment magnitude scale, which is based on just the total amount of energy released by the earthquakes. We use the Richter scale more often. You hear that more on the news and everything. It's a scale of 1 to 10, 10 being just total destruction, 1 being you could barely feel it. Your book has a great chart on there that kind of explains what kind of damage happens at different Richter scale measurements and what it would feel like. A couple things about the damage from earthquakes. We talked about aftershocks. All an aftershock is when an area has a large volcano, a large earthquake. When that earthquake releases the stress afterwards, there are several earthquakes that do occur at a smaller magnitude, but enough to cause a lot of damage. The aftershocks are dangerous because the first earthquake coming through shakes the buildings and kind of takes the foundations and breaks them up a little bit, but it's the aftershocks that take the weakened building and maybe do a lot more damage. There's also something called liquefaction. Well, that's kind of it's a weird thing, but the ground actually shakes so much that it almost acts like a liquid. Mexico City was an example of this back, I believe, in 1980 or 81. Mexico City is built on a dried up lake bed. Well, the ground shook at such a vibration that the ground itself almost acted like a liquid, and some buildings sank into it, some buildings just crumbled. They thought they had built it on firm ground, but they didn't. One of the worst effects could be this thing called a tsunami. Tsunami is just a huge water wave that's made from either an earthquake or an underground volcanic eruption or a volcanic eruption near the shore or a landslide underwater. These tsunamis move really quickly. They can travel thousands of miles without weakening. The problem with that is most people can't see it. It doesn't look like anything. I have an animation here kind of talking about the tsunami that happened. There was a tsunami that happened in the Indian Ocean in 2004, and this video right here kind of explains what's happening. Stress built up, sent water up in 150 miles offshore, releasing the energy in waves. Some of these videos in this little animation, if you pause it and read this, it's quite interesting. All the information that's given here. I'm going to just kind of scroll down slow. I'm not going to read it for you, but you should read it. It's quite interesting. I'll show you this other second video here. It's kind of what it looked like when it happened. It sent the water up. Here's Sri Lanka. This is the one that got hit with the big wave. These guys got the reflect, the wave that didn't have to travel as far. Here's what it would look like in the open ocean as the waves coming through. There it went, right there. It might not look too bad. It travels at about 450 miles per hour, but it may only look 2 or 3 feet high in the water. Now when it hit the shoreline, this is kind of what it looked like. Built up, and the wave crashed along the shore. Now it was, they say, about 10 stories high, and it was only traveling 30 miles per hour. But when you see a wave coming in, every wave has 2 parts. It has a trough, which is the bottom part, and the crest here. But if you read through this, the seabed dropped nearly 6 feet in that earthquake. Here's an example of the video. Just notice the wave gets pulled back, the water gets pulled back to feed the tsunami wave. And then as it comes in at 30 miles per hour, it just inundated, it just covers everything. And then there was something called the wraparound effect here. You can see as the water pulls back, all the damage that was left behind. But you can see the waves coming. This is where it started. It's coming, hits this island, but then it starts hitting some of the landscape around here, and it bounces off, and they get this kind of wraparound effect where it wraps around the island, and the backside of the island actually gets hit along the way. Now, how high did the wave get? Right where it started at the epicenter, you can see that this is about 400 to 1700 centimeters. By the time it got to Sri Lanka, right here, it was about 200 centimeters. That's about 2 meters, actually about 2 meters, 3 meters, 56 feet tall here along the coast of Thailand, which is up here in Sumatra. That's a pretty big wave. And then how far did it travel? This is the crazy part. In an hour, it traveled that far. In 8 hours, it hit Madagascar. Traveled 3,000 miles in roughly 7 hours. That's about the speed of a jet airliner. If a plane took off from Indonesia and flew to Madagascar, they would both get there at about the same time. So that's the part that's kind of crazy. Now, what can we do about this? Well, scientists learn everything that they can about earthquakes. They measure them, they record them, they learn about them, they follow the seismic activities on faults all around the world. We can try to build structures that are a little bit more resistant to earthquake damage. Sometimes we build them with these things called cross braces. You can see the X's here that these buildings have built. These are meant to try to support them a little bit more. Sometimes they build sand pits, moats, kind of like a castle, but it was full of sand around the outside to absorb some of the energy from the earthquake. Sometimes I know that in California, some of the buildings, I think even in the Capitol building of Sacramento, California, they actually have it built up on huge springs that sway back and forth to try to absorb some of the movement on the ground. Well, all of that's nice, all of it can help, but nothing has been made that is totally earthquake proof. But there are steps we are learning. That's all we have right here. So the main things we got to get out of this is, we'll move back real quickly. The Richter scale is what we use to measure the earthquakes on a scale of 1 to 10. Aftershocks are earthquakes that happen after larger earthquakes have happened in the area. They cause a lot of the damage because everything's weakened already. Liquefaction is when the soil, the ground actually starts to be shaken at such a frequency that the ground actually acts like a thick soup. Tsunamis are created by earthquakes, volcanic eruptions, and landslides underwater, where a large wave of water is triggered, and they move quickly, and they can go thousands of miles without weakening, and they really can do quite a bit of damage, and in property and in loss in life too. Scientists, what are they doing? They're studying them. They're trying to learn from them. Sometimes we know when they're going to happen. Sometimes there's no evidence at all. It just happens. What can we do? We try to build structures that are a little bit more resistant to earthquake damage. We build cross bases. We put buildings on springs. We surround buildings with sand to try to absorb some of the energies from the seismic waves. But that's what you have to get out of it. So, oh yeah, and the first person that can come up to me and give me 2 things that we can do to make buildings resistant to earthquake damage, I'm going to give you 3 falcon feathers. First person in each class. Thank you.